Boy, that green marker is very hard to see. For being a fresh marker.
That's Stephen's hand.
No, it's mine.
Yours?
Yep.
I assumed it was Stephen's because he writes things before all the time.
I write things on the boards all day long.
I know, but he's not his job. He just does it.
Sure, gotcha. Alright, we're moving into chapter 12. So everybody open up the book, chapter 12, page 340. We're going to introduce something, and I've been saying this for quite some time, that this book is a very, very, very good book, and a very, very interesting read, and very, very helpful read. 340 to 540. What did I say? 340, no, sorry. So this chapter, if you flip back one page, is chemical kinetics. Now we did talk last year about, there was a chapter we talked about with kinetics. I don't know if you guys remember reaction mechanisms and rate laws and what else? Elementary steps and all that stuff. That's going to be, we're going to see those again in this chapter. We are going to go significantly deeper than we did in regular high school chemistry. We're going to do some stuff with Excel. Oh, that reminds me. How many of you have a computer that has Excel on it? Oh, please say more than none. How many of you have a computer with Excel on it? I'm assuming it
Do you
does.
have Word and PowerPoint? Microsoft PowerPoint and Word? So you probably have Excel as well.
You have an HP laptop, right?
Yeah.
Then you're not.
Probably.
Okay. Well, can you guys figure that out if you don't know? Because I don't think Google Docs is capable of doing it, but I can look to try to figure it out if it is. The reason why I say that is you're going to have homework where you're going to have to use Excel or some alternative, and you're going to have a test where you're going to have to do that. Well, I have a computer here and a laptop that has Excel that I can bring my laptop in for your test. But if some of you also have computers, that would be ideal. Sure. Okay. That makes sense. Okay? I had to figure that out sooner rather than later because it's coming up real quickly. Probably by Monday. Alright. So back to 540. We're going to read the first introductory before we get to 12.1. And just to keep Emily engaged, I'm going to make her read it.
Wait, what paragraph?
The whole thing. Up to 12.1.
Okay. The applications of chemistry focus largely on chemical reactions, and the commercial use of a reaction requires knowledge of several of its characteristics, including its stoichiometry, energetics, and rate. A reaction is defined by its reactants and products, whose identity must be learned by experiment. Once the reactants and products are known, the equation for the reaction can be written in balance, and stoichiometric calculations can be carried out. Another very important characteristic of a reaction is its spontaneity. Spontaneity refers to the inherent tendency for the process to occur. However, it implies nothing about speed. Spontaneous does not mean fast. There are many spontaneous reactions that are so slow that no apparent reaction occurs over a period of weeks or years at normal temperatures. For example, there is a strong inherent tendency for gaseous hydrogen and oxygen to combine. But in fact, the two gases can coexist indefinitely at 25 degrees Celsius. Similarly, the gaseous reactions are both highly likely to occur from a thermodynamic standpoint, but we observe no reactions under normal conditions. In addition, the process of changing diamond to graphite is spontaneous, but is so slow that it is not detectable. To be useful, reactions must occur at a reasonable rate. To produce the 20 million tons of ammonia needed each year for fertilizer, we cannot simply mix nitrogen and hydrogen gases at 25 degrees Celsius and wait for them to react. It is not enough to understand the stoichiometry and thermodynamics of reaction. We also must understand the factors that govern the rate of reaction. The area of chemistry that can concerns reaction rates is called chemical kinetics. One of the main goals of chemical kinetics is to understand the steps by which a reaction takes place. This series of steps is called the reaction mechanism. Understanding the mechanism allows us to find ways to facilitate the reaction. For example, the Haber process for the production of ammonia requires high temperatures to achieve commercially feasible reaction rates. However, even higher temperatures, more cost, would be required without the use of iron oxide, which speeds up the reaction. In this chapter, we will consider the main ideas of chemical kinetics. We will explore rate laws, reaction mechanisms, and simple models for chemical reactions.
You find reading a science textbook, you find that there's a lot of big words that you have to read. Okay, all right. Interesting thing that you saw out of that little short blurb. Nothing in there. You find interesting?
How would adding iron oxide help at all?
It's a catalyst.
Oh, okay. It forces it to come close together and fine.
I don't exactly know how that catalyst works. There's quite a few ways for catalysts to speed up a reaction, but yeah. What else? So it seems to be good at chemistry to understand the importance of commercially producing things is more than just having a one-layer knowledge of something, right? It's not just good enough to know stoichiometric calculations. It's not just good enough to know how much reactants and products you have. If you can't just put reactants together and poof, you get a chemical reaction. There's a lot of things involved. They actually gave quite a few situations where it was thermodynamically favorable, but they didn't see anything. And why was that? Yeah. So you could have an exothermic reaction that is very, from an energy standpoint, favorable, but you won't see virtually anything over the period of a significant amount of time because of how fast the reaction occurs.
Would activation energy play a role?
Absolutely, that's where we're
Like-
Yep.
You can mix oxygen and like gasoline vapor all you want, but
Yeah.
there's a spark. Nothing
Yep,
happens.
absolutely. Yep, and that's a big part of this particular chapter. You can have something that has an energy curve that like it starts here, has a hump, and then is really exothermic. But if you can't get it over the activation energy,
So, like my example of gasoline and oxygen, it's oxidation is burning, right? It's oxygen's reacting with
Yeah,
the
okay, yeah.
new stuff.
yeah.
So is it the spark is the first one, and then it's a chain reaction of
Yeah, usually once you get the spark, it has enough energy when it's giving out products to keep the reactants,
so it's
to fuel the reactants to have enough energy to continue to react.
the energy for it to react comes from past
Yep,
reactions.
so that when the products are produced, it's very exothermic, that the energy given off is used to fuel the continual
next
reaction. Yep,
Okay.
absolutely. Okay? I think the most interesting thing about this is what's italicized. And when it talks about spontaneity and it says spontaneous does not mean fast. That's a really important concept to get. Just because it's spontaneous or likely to occur from a thermodynamic process does not mean that it's fast. Okay? That's very, very important. So really what this whole chapter is dealing with is the idea of kinetics. And kinetics deals with a lot of things, but I would say the main thing it deals with is how fast or rates of reactions. Okay? Along the way, we'll find out that a way to determine how fast something reacts is to know the steps that react. Okay, we're going to get to the point where we'll talk about you're only as fast as your slowest step. I don't know if you guys remember from last year, rate determining step.
Yeah.
Okay, so we're gonna talk about the steps. We're gonna talk about the reaction mechanism. We're gonna talk about how the slowest step affects whether how fast the reaction is. The difficult thing is figuring out the reaction mechanism of something is very difficult to do because it happens like that usually, and you don't see all the steps. That you just see the beginning and the ending. That's why it's a lot easier to just focus on energy and whether or not it's spontaneous or not, because you can see at the beginning and you can see at the end, but you can't always see what happens in between. In fact, you very rarely can. Okay? So, kinetics is really the area that studies reaction rates, and there's a lot that is embedded in that. Okay? All right, so let's say I have this reaction, which we're going to kind of look at this reaction with a couple of charts in our book to kind of unpack this. And I'll try to ask this question in a way that, that you can answer. Okay, so here's a chemical reaction. A big part of figuring out rates has to do with concentration. So if I started with a certain amount of reactant, so let's say I just got 100 grams of that reactant, and I began reacting it, what could you say over the course of time would happen to the concentrations of your reactants in your product? Could someone walk me through what would happen to the concentrations of reactants and products over the course of time while it's being reacted? Did I do something that balance? Oh yeah, it's balanced. 2 oxygens, 4 oxygens, 4 oxygens.
Oh, I was thinking 202.
Right. Did you hear my question though that I asked you guys?
Yeah.
Can anybody walk me through if I start off with a certain amount of reactants and I begin reacting, what's going to happen over time to concentrations of each of these guys?
Right.
What will decrease? Of both? Of everything? Of one thing? Of what?
Well, the reactants will.
Okay, so the reactants concentration over time will what? Go down. Okay, what about the products?
Go up until they reach equilibrium.
Yeah, the concentration of the products are going to go up. And you're getting a little ahead of yourself when you're talking about equilibrium, but the answer is yes, it eventually will reach equilibrium. Eventually, we will do this. And we will say that it's reversible. We will say that eventually, as the concentration of this goes down and the concentration of this goes up, the rate in reverse will start to speed up, and the rate going forward will start to slow down until it reaches what? Equilibrium. We aren't going to get to that. Okay? At this point, we're going to kind of assume that it will go mostly to completion for the sake of being able to study reaction rates.
Well, if you can remove the product as it's reacting,
Yep, that helps.
It'll always go to completion. Usually.
Well, you would never get to completion. If you kept removing, it would just keep going. Until, I guess until you ran out of reaction.
Okay,
Sure. All right, another really important thing here is you could talk about these coefficients. Okay? You could say that the rate at which this is going bye-bye is the same rate at which this is being produced, but it's not the case for these guys. This would be reacting twice as fast as this is getting produced based on the coefficient ratios. Does that make sense? This is important because there's a test question on this concept that everyone has gotten wrong every year I've taught, except for maybe 1 or 2 students. Mental note. I'm not going to tell you the question, but it has to do with this idea, how the coefficients affect rates. Okay?
Show us that testing it.
Okay? Okay, so chemical kinetics deals with the speed at which these changes occur. In a chemical reaction, the quantity that changes is the concentrations of reactants and products. Okay? Now, they have this, so this would be just a generic rate law for being able to determine the rate of something. This is just saying the rate is going to be dependent upon how much your concentration changes as your time changes. This T is not temperature, it's time. Maybe it should be small t. If you want to change it to small t to make it a little easier for you to remember that it's dealing with time and not temperature, that might be a good idea.
Is it usually in seconds or no?
Yes, absolutely will be in seconds. Good question. Another thing with this is we're going to, for the most part, deal with some simple problems where we only have one reactant. So I could write the rate law of this and just put the reactant in here. Okay, you could find the rate at which products are being produced as well, but most of the time, for the sake of what we're doing in this chapter, we'll be focusing on the rates of reactants. Okay, and if you look in your book, turn to page 542, 543. Okay, your book talks about how, depending upon whether you were talking about reactants or products, your rate is going to be either positive or negative. Does that make sense? Like, what would your rate? Would your rate for reactants be positive or negative in the context of common sense? Negative, right? Because you'd be losing reactants. Okay, assuming you don't start with a certain amount of products, you start with all reactants and no products. That's what we're going to assume a lot of the times. Okay, and your products rate will always be positive. Okay, now your textbook decides to define every rate as a positive rate. So really what they do is they usually plop a negative sign on when you're doing rates for reactants so that it gives you a positive number. Don't get confused here, because it's really important that we're still talking about reactants, which we know in the context of a chemical reaction is going to be decreasing, right? Because you're reacting it. You don't get confused with that, okay? Let's look at a couple of these tables here. This is ACT 101 here, being able to look at a table, look at a graph, and be able to deduce some important information. Let's start with the graph, with the green and the blue and the red lines. Okay? So let's just quickly look at the x and y axis. Your x-axis is time, your y-axis is concentration. So it's essentially the change in concentration over time, which we would define as the what? The rate. How fast the concentration changes over time. Now this particular graph is the graph of 2NO2 going to produce 2NO and O2. Okay? And if you look, two of those lines look very identical but inverted. Which two? Green and blue. Okay? The green represents this, and the blue represents this. Why does that make sense? They have the same coefficients, which means the rate that one gets produced is the same as the rate at which one gets reacted. So from a rate standpoint, they look identical. The only difference is one line's decreasing at the same rate as the other line is increasing at the same rate. Everybody see it? Okay, so then you look at the red one. Also makes sense why you see two rates increasing, because you have how many reactants? Two. Okay? And if you look at the red one, you can see that it doesn't quite, you don't quite get as much concentration over time. Why is that? Yeah. So essentially, I get twice as much of the NO over time as I do O2. And you could probably make that deduction by looking at that it's half, or the rate is half. Okay? Now, something that we will get into, not today, but we will get into, does everyone see those tangent lines that are running on all three of those graphs? Everybody see that? Yeah. Okay? The reason why that's important is, none of these lines are straight, are they? Which means that none of the rates are constant. Does that make sense? From a mathematical standpoint. Which means the rate is ever what? Yeah, changing. Either increasing or decreasing. Okay, and this should make sense from what we remember from equilibrium. Okay, let me kind of see if we can revert back to what we know from equilibrium. Okay, what do you guys remember about equilibrium from a rate standpoint?
It's when both sides are reacting at the same rate.
Yes. So equilibrium occurs when the rate of the forward reaction equals the rate of the reverse reaction. Do you remember me saying that multiple times in the past? Okay? Well, if I have 100% this and 0% this, it's 100%, the rate is all going forward and there's no rate going backwards. Does that make sense? Okay? Well, as I start to lose some reactants and increase my products, is after I start losing some reactants, is my rate gonna stay the same?
No.
What? My rate's not gonna stay the same. We could go back to, do you guys remember the collision theory at all? The idea that what causes a reaction is when you have enough energy, you have collisions, okay? All right, well if you have less stuff, are you gonna have as many collisions? No, so therefore your rate's gonna slow down. Correct? Okay? So the rate of the forward reaction is gonna start slowing down and the rate of the reverse reaction is gonna start speeding up, and isn't that what you see here? It's not constant rate, it's an ever-changing rate. Well, this makes it a little bit more difficult, doesn't it? Okay, so I don't know where all you guys are all at from a math standpoint, but what is the tangent line doing here?
Tells you the rate of change of that.
Yes, it tells you the rate of change at that one point. If you take a line, tangent, which just means it's a straight line that runs through a curved line at one point.
Oh.
If you find the slope of that straight line that runs through the curved line at that one point, you can find the instantaneous rate. Okay? Now, we're not going to do too much of that because that is very calc-based, which I know all of you are proficient in calculus.
I've never done
Exactly. Okay. I'd like to teach calculus someday, because then I can actually learn how to do it and know what I'm doing. It's been a long time since I've done calculus. I remember bits and pieces of it, but that's about it. Okay. Just note that that's the purpose of the tangent line. And we will get into instantaneous rates. We're actually going to take each of these rate laws and we're going to put them into a linear relationship, and we're going to be able to determine what kind of rate we have based on being able to do linear regression and seeing which line fits the data the best. And that's what we're going to do on Excel. You're reading this? Gosh!
Talks about her dad bringing more.
Wait, can I read it?
Don't read on the camera.
Not the whole thing. Oh.
This is our future lessons that are watching this when he's gone.
You're not even engaged. This is actually, to me, one of the more interesting
I was
lessons.
engaged.
Hello,
There's
future
so many
students.
countries.
Uh-huh.
Kramer is currently sick. Enjoy the video. Hello.
They can see me.
I know. He's not sick. He's stuck in a computer. Destroy the computer. Save him. Help him escape.
All right. And so if you look at table 12.2, you can see it actually gives you the rates under various different time changes. And notice that the rate of your reactant steadily goes down. Okay? There's going to be quite a bit of equations this chapter. A lot of equations. Hence why I will give you an equation sheet for this test. Which will include, so there's your equations for the two chapters. It's a lot. Okay?
I recognize a few of them.
Most of them are from this chapter. Okay? But what we're gonna do, and again, please, if you guys can check, how many of you know for sure you don't have Excel? Just him? You don't for sure? You probably not. Even at like your home computer?
Oh, sure.
Because the only thing I'm worried about from a standpoint of is homework.
No, I do at a home computer actually.
You do have it at a home computer?
Yeah.
Because I can maybe work something out to get enough computers, or we can do it over a period of time, that I could have my computer and a laptop, and we can just kind of take turns cycling through. So, please, you're,
Do you have work?
so what I want you guys to do, add to your homework. Can you on 12.1 write next to your homework? Figure out if you have Excel at home or on some device, and that's your homework.
That's
Well, you have to do the other problems, yes. But I need to make sure that so I can plan accordingly for, because we are